Hi everyone, and welcome to this new video about steady state analysis, and we continue with our design examples. This is our design example number 2 about RC circuit design. In this example we would like to design the following. Design this circuit to produce the output voltage Vout, which is 8.23 cosine 2000 pi t minus 23 degrees volts, when provided with an input voltage of 10 cosine 2000 pi t in volts. So as you can see, again, we have the rating frequency exactly the same for the input and the output voltage, which is mandatory for steady state analysis. In addition, we have the high frequency gain of 1/3. So we have 1/3 as a gain at high frequencies. So that's actually the given data. So how do we start? As we did also in the example number 1, design example number 1, we would like to determine first the transfer function. From transfer function we can go using the amplitudes and all the phases for the input and output voltage, and also in this case high frequency gain to determine the component values R1, R2 and C. So that's actually design, so we have to determine those 3 components. Okay, so let's move on with the transfer function first, and I will do that again as we did in the previous example, design example, in Laplace domain, and I will transform that later on in the j omega domain. So first the transfer function. How do we do that? As we did in the previous video, we use the voltage divider rule. So we check V out divided by V in is actually this impedance, which is shown here, divided by the total impedance seen by the source. So if I now write down the expression for the transfer function, h of s is V out of s in Laplace divided by V in. So if I now designate this, so I make a new impedance, so I will call this, for example, Z1. If I have now the Z1 designated as shown here, that will be, voltage divider rule will be Z1 divided by R1 plus Z1. That's just a standard voltage divider rule. Okay, so what is Z1? That's actually, in this case, it's just a series connection of R2 plus 1 over SC, because I use the Laplace parameters S. So if I now substitute this in this expression, so what do we have? We have the following. H of S will be R2 plus 1 over SC divided by R1 plus exactly the same as Z1. It will be R2 plus 1 over CS. I can simplify this expression by multiplying the numerator and denominator by SC. So that will result in the following expression will be 1 plus R2 CS divided by 1 plus R1 plus R2 times CS. That's actually the expression what we have for the transfer function. Now if I now make this substitution, so I will use S is equal to j omega. I can use that in steady state analysis only. Then this expression will transform in the following. So this will be h j omega will be 1 plus j omega R2C divided by 1 plus j omega R1 plus R2 times C. Okay, so that's actually our expression. We have now the following situation that will be handy when we write it down first. At omega 2000 pi radians per second, we have the following information given. We have a gain, let me write it down, we have a gain of 8.23 divided by 10, which is actually at this frequency we have a voltage source, voltage amplitude of 10 volts going in, and it will result in 8.23. That's actually what it is. So that will mean actually gain at this frequency only is 0.823. The phase at this frequency, only at this frequency, will be minus 23 for the output, minus 0 for the input, will be minus 23 degrees. So I have now two situations, two given data, 1 and 2. For the gain, I have this, and for the phase, I have this. It will be handy. Of course, I have also the high frequency gain. Let me write down also, but it is not on this frequency. So for omega approaching actually infinity, I have a gain of 1/3. Okay, that's actually this situation. What do I need to do now? Because this is a gain and it is a phase and it's also a gain, I have to use the expression for the gain and also for the phase for this transfer function. So this transfer function will result in an expression for gain and also an expression for the phase. So the expression for the gain for this h of s will be h of s, the magnitude of that will be the magnitude of the both sides, so the magnitude of the top side and the magnitude of the bottom side. So it will be have the following: the square root of 1 squared, which is just 1. I will make it clear, 1 squared plus omega r times c quantity squared in total, divided by exact same procedure, 1 squared plus omega times r1 plus r2 times c, I will make a room here, times c and the quantity also squared. Alright. And for the phase, this is gain. By the way, this is gain. So for phase, we have the following. Let me write it down also for the phase. We have the phase, which is phi as a function of omega, will be the phase contribution of this part minus the phase contribution of the bottom. So you have the top part, so the term here, minus the phase contribution of this term. So that will be actually arctangent of omega r2. So this will be imaginary part divided by the real part. So it will be omega r2c divided by 1, which is just omega r2c. And I have to do minus the phase contribution of this part will be again imaginary divided by the real part. In the arctangent expression will be omega times r2 plus r1 plus r2 times c divided by 1, again only the imaginary part effective. So that means arctangent, let me make some room, will be omega times r1 plus r2 times c, all of them in arctangent. Now I have now two expressions actually for this quantity, for this transfer function. I've made the expression for the gain and also made the expression for the phase. Okay, so what do I do next? I have to determine, of course, the component value. So I have three unknowns and I have to determine those unknown values. What I also need to determine is the high frequency gain. I have to use this information also. So if I now look at the circuit, just practically, I can say the capacitor will be at very high frequencies, say 1 gigahertz, 1 terahertz. There will be a short, practically. So that means actually the effective circuit will be R2 divided by R1 plus R2. You can also see that here in the expression for the transfer function, or here, make omega, for example, infinity. This one will not have any effect. Also the one here will not have any effect because omega is infinite. That will be actually, this term will be much larger than this term, and this term will be much larger than this term. So you will actually have in effect j omega r2c divided by j omega r1 plus r2 in parentheses times c. So c omega j will cancel each other out, and you will have r2 divided by r1 plus r2. So actually you will see it exactly the same in a mathematical form and also in the circuit if you just consider the capacitor as a short when you have very high frequencies. So I can say the following. I can say, that's also very important, I can say this will result, so at high frequencies, this will result actually in the following. H of omega will be at, of course, omega approaching infinity will be R2 divided by R1 plus R2. And this must be 1/3, so 1/3. So I can say the following about this. If I now rewrite this circuit, I mean the expressions, I will have R1 plus R2 is equal to 3 times R2, and this will be R1 plus R1, I mean, is equal to 2 times R2. So this is actually a very interesting result, and this will be our first equation. So R1 must be 2 times larger than R1 must be twice R2. So if I have the value of R2, I can just calculate the value of R1. It's actually a very simple expression for the first equation. So what do I do next? I can do the following. I can now substitute the value for the omega in this expression, also in this expression, and express this, of course, equal to 0.823, and also the phase equal to minus 23 degrees. So then I have another equation, and I will set up the equations for that, and I will determine then using the equations we have now, the component values. So the next step is just substituting the values for the omega in the expression for the magnitude and for the phase. So what do you have? I have the following. I will substitute the value for omega. So I have the following. Let me move on with black. So I have h at j 2000 pi. The value of that will be square root of 1 plus 2000 pi times R2C quantity squared divided by 1 plus 2000 pi R1 plus R2 times C quantity squared will be equal to 0.823. That's actually what it is at this frequency only. Now for the phase expression I can do the same. So I will have arctangent, so that will be at this frequency 2000 pi. I have arctangent of 2000 pi R2C minus arctangent 2000 pi times R1 plus R2 times C, and that must be equal to minus 23 degrees. So I have now two equations. Let me also make equation number 2 here, and also this equation number 3. So I can now use also these two equations. Let me a little bit zoom out. So I have now additional equations. So this can be also used to move on to calculate the required component values. So what can I do now? Now, the problem actually is what we have is the following. We have R2, R1, C, 3 unknowns. Exact same problem is here. So what I have is I need an additional unknown, so additional equation that will be actually used here. So if I now look at this expression for this one, R1 plus R2 is 3 times R2. I have this one also here, so I have R1 plus R2, which can be substituted by 3 times R2. If I do that here, or here, doesn't matter. So I have actually the following. So if I now set or use R1 plus R2 is equal to 3 times R2. That's actually what I will use in the expression for the phase. So I will have the following. I will have, so the phase, let me just start with the arctangent. So the arctangent will be 2000 pi times R2 times C minus arctangent times 2000 pi times 3 times R2 times C, that will be equal to minus 23 degrees. What do you see? I see the following. I see the exact same unknowns in product form here and also there. So I can now make the following situation. I can now say set x equal to R2 times C, just a new unknown. And I will now use this unknown parameter and I will calculate the value of this one. Since if I know this, I can just continue with my work. So I have the following. R tangent (2000 pi x) minus R tangent 2000 pi 3 times x will be minus 23 degrees. Now you can try to solve this. It is not really simple. So you can use a solver for this, and if you do that, you will give you x is equal to very close to 4 times 10 to the minus 5. And this is R2 times C. Okay, this is actually the situation what we now have here. So I have a value for x, which is just a product of R2 times C. And I have this equation here. So I have, in fact, 4 equations. So I will make this also equation number 4. The problem now is the following. If I now use this equation, I have now used, of course, the equation for the phase, and I came up to this value. If I use the same procedure for this one, so R1 plus R2 is equal to 3 times R2, substitute it in here and solve this equation, I will get the exact same result. So we have the following problem. I get the same x value no matter what I do with this equation or that equation. So I don't have two different expressions for R2 times C. So that will lead us to the following step. I have to choose one of the component values. So if I now select one of the component values, I can now calculate the rest. So if I now select, for example, in this case, not the C for the change, I will make R2 will be 1000. So it will be 1000 ohms, 1K. Then I can say, if I now have R2 is 1000, I can now use this expression, R1 is 2 times R2. Then I can say R1 is 2 times R2, which is 2 times 10 to the power 3 ohms. So I have now actually 2 unknowns already. And for using this expression, I can now calculate the capacitor. So then the capacitor C is equal to X divided by R2. I know X, which is 4 times 10 to the power minus 5, divided by R2, which we have now is 1000, just select that value. And this will result in C is equal to 4 times 10 to the power minus 8 farads of, if you want to write it down in nanofarads, it will be 40 nanofarads. So I have now four parameters already calculated. One, of course, chosen, R2, and the rest is calculated. So R1 will be 2 kilo ohms. R1 will be 1 kilo ohm, just a summary here. And the C will be 40 nanofarads. And it will actually conclude this design example. As you can see, we have set up the equations for the phase and also for the magnitude, so for the gain. I have only used the expression for this, for the phase. You can also use this, try it for yourself. You will have exactly the same expression for the x. X will be 4 times 10 to the minus 5. You have to choose one of the component values. So we don't have actually a unique solution. So we don't have 3 unique equations. So it will actually lead to one selection of the components. So actually this is for the example number 2, design example number 2 about RC circuits. We continue with the rest of the design examples, so keep in touch and see you next time.